stay here very briefly. So I'll just stay here very briefly before I hand over to Margaret to introduce Mauricio. But on behalf of the Society, Mauricio, thank you so much for your time and for attending to give us this presentation. It's great to have a man of Manchester here as well, as I am one of those. And thank you everybody for attending, and over to you, Margaret, for the formal introduction. Thank you.
Welcome all, it's lovely to have you here. Dr. Mauricio Vieira Kritz is a pioneer in computational science and mathematical modeling. He currently serves as a senior research fellow at the University of Manchester and is a professor within the multi-institutional graduate program on knowledge diffusion. That's in Brazil. Blending expertise in informatics, mathematical physics, statistics, and living systems, Dr. Kritz was a central figure in establishing the National Laboratory for Scientific Computing, LNCC, in Brazil. His career underwent a transformative shift towards field research in the Amazon, prompting him to move away from traditional physics to develop new frameworks for organization information theory and biological complexity. A polyglot, you don't want to know how many languages he speaks, and a proponent of tam mathemata, sorry, that's the Brazilian version, isn't it? The philosophy that mathematics is inherently wired into the human mind. He currently investigates how biological brain characteristics impact scientific creativity and transdisciplinary collaboration. It's a real pleasure to have you, Mauricio. Thank you so much.
Thank you for the invitation, and thank you, Peter. And I thank you, Meg, for all your support. I wouldn't be able to cook anything in 15 days were not for your help. So let me follow before anything. After some events of this morning, I would like to clear a few things. So some communication traps that we have been immersed in. So, for instance, what I understand for a schooler, my examples is Ernst Mayr is a biologist and Feynman, and not Einstein, because I think Einstein mixed up nature, reality with the description of reality. And knowing something is not knowing its name. You have to go further. For instance, knowing an electron you need to go to the equations to see what an electron is. It's very difficult to do it otherwise. So, and that's the reason. And so I'd like to tell you that information is a messy word, and we have two formal definitions that are Shannon definition, that is a measure, and Shannon never considered that to be information himself. But anyway, as a measure, and I have Komogorov charting that is more or less tied to coding. And I have my own information, and that's why I insist in writing it this way, to clarify that there's another idea, and it has nothing with communication channel. It's associated with, but it's not dependent on the idea. And to see how all these three ideas of information is different, I just considering the following example. You'll be off tomorrow, and you leave a message in the secretary table, your secretary table or department secretary table, saying that you'll be off for one day. And so, and this is an information. You sent a message. We consider that as an information. But try to fit it in Shannon's measure or Komogorov-Chaitin's idea or my own idea. It doesn't work. None of the three is able to consider this message as what is considered information in these three frameworks. And of course, we were discussing a few minutes ago, a few hours ago, Shannon measure is Wiener's measure in Brillouin's measure, but in Brillouin is considered to be negative entropy, negentropy, and they are related only by the equation. The idea of negentropy has nothing to do with what is considered as information in either framework. So this is the problem. We are in a very slippery hold. The same with organization. We have to observe that organization's word is used for the process of organizing things, and it's not the case. And my definition, it is based in a quintessence, what we call quintessence of organization, and in the sense that all organizations do have the properties that are represented in the model. We'll see that later on, okay? So if you have any doubts about the meaning of the words I'm talking, please ask, okay, to prevent further problems. So I will start, before reaching the outline, I'll start with a brief description of the ways, just to explain the title. You know? So sources of human knowledge, we have religion, we have church, it's not the same thing. In religion, you have one source of knowledge that is mystic or something like that. One interpreter that tells everybody what is to be understood. And this picture is good for the Indians in the Amazons and for many sects in the Hindu sects and things like that. And the church, in general, you have something organized. And basically, we have four churches in the world: the Jewish, the Catholic, the Muslim, and the Buddhist. And then there are a group of people that are really the owners of the knowledge, and they then share totally or partially with the rest of the people that is behind them. Or the other way is philosophy that come in the Greek style. So that come from dialogues between people, and people discuss things. And then we have science, when that it comes from the same Greek philosophy of acquiring knowledge about the nature. But in this case, we have one element to discuss with, that's nature itself. And this nature is queried by experimentation, okay? And then we have I'll be back to this picture in a while. So, but these are the main sources of knowledge you have. And science, we query nature by making experiments, taking quantification things and not, you know. So that's I don't have the slides here, but sometimes we need to use non-numerical, non-quantifiable knowledge to decide what is the appropriated fitting of the data. And the curve that fits the data is already a model, see. And then I think that we have observation in science. We have a sort of comprehension or a compact description of what we have observed. And over these models, we state things that we consider true. And the means we have to do that are completely different from one discipline to another, sometimes it's culture dependent. But anyway, that's the way I put it in a very simplified manner. Okay. So, but the important thing is that from the Greeks to the Renaissance and the scientific revolution, the pure thought changed from purely deductive, inductive, including the abductive. And to exemplify that is the insight of Archimedes or the Kepler's jump when they decided that the data that or the planets were not really circles but conics, and then this is kind of abduction, and it took Kepler 20 years to reach this conclusion, okay? Making computations and so on. So, but how did this happen, you see, is a part of the things that I'm trying to model and understand. So, of course, there are basic mathematical things that are developed along the time, and different philosophies and cultures that are behind that or associated with them. It's difficult to extract any causality here. But to what I will discuss this after one is the communication. So in the Greeks were personal dialogues. Okay, so after Gutenberg, we had the printing, so and letters too were used too. After Gutenberg, we could print things, books and articles and things like that. And it took a while to go this way. But there were the societies and the discussions with peers, and everything was spatially constrained for obvious reasons. So we don't have that. And at the same time, the problems that were addressed by scientists in general could be represented in Weber's classification as problems of simplicity. And then during the Enlightenment, the mathematical the probability theories and statistical methods, we came to the disorganized complexity, how it's called in Weber. And there is one thing here that is very important, is not well noted everywhere, is that we have the aspects that we observe here are local, pointwise for velocity of a particle, and things like that, or the mass of a particle. And here, the aspects observed are collective. For instance, there is no sense in talking about the temperature of one particle, one molecule. There is no sense in talking about the pressure of one particle or one measure. These are things these are observations that do require a large amount of interacting elements, okay? And then in the 20th century, we came to the organized complexity problems. And even more, I'm in the process of developing this, but there is here this who is, let me amplify this here for you. So who is, this is mine. So in the sense that everything that is here, for instance, this is landscape ecology, and you have multidisciplinary research, but the disciplines relate to certain phenomena, that is natural phenomena. And for instance, physics, chemistry depends on physics. So, and biochemistry depends on chemistry, biology depends on the findings of biochemistry, and so on. So, and the things that are exchanging in each interaction, they change from one level to the other level. So, in this level is just a way of representing things. It's not really causality. Is the dependence is much looser than that. Okay, so this is why the servants of nature come in, and now we have the global challenges. Okay, we have the global challenges that phenomena that reside here and involve all disciplines and all kinds of phenomena. And this is my definition of which is a global challenge. Some examples here. But then the underlying phenomenon need to spread in large spaces, in continents or transcontinental extensions. The underlying phenomenon that is associated to the challenge, okay? The challenge is we need to understand the phenomenon to be able to know what to do. That's the point. So the underlying phenomenon belongs to the organized complexity class in general, okay, but not necessarily. But even when we talk about climate, just climate, and that is apparently is close to physics and chemistry. It's just a part of it, because there are things in the climate that depends on the biology of the Amazon region and the biology of the deserts in Africa. And there are connections between the Amazon and the deserts in Africa. It's a very, very interesting thing. And underlying phenomenon occurs at several time scales, space scales, and organization scales simultaneously. This will be clear later on. And the institutions, the rule of the game, while dealing with, for us to interact and deal with this phenomena, change both in space and time. Here is wrong. It should be stakeholders. And for instance, in sustainability, you have to decide what to sustain. One of the most curious papers I read in my life was a paper promoting the sustainability of the coal mining industry, which is one of the most damaging industries for nature that exists. And then you have to decide upon that before talking about these things. So now is my outline. Okay, the things I will tell you all related to cybernetics, and but they are closer to this meta-cybernetic picture of forgot the name, sorry. and then the traditional ones. The first, I'll talk you a little bit about myself. The two first, this will be very fast, and because um, you asked me to do that, so I'll talk about that. And then I'll talk about organization information theory, information theory, and then what we can do with that, why it enters in the modeling of the Amazon region. And I'll be back to the scientific milieu. That's the thing that I'm doing now, that I'm interested in now. So first of all, when I left college, I didn't want to be a scientist at all, but I wanted to learn statistics. And then there were no school of statistics in the postgrad level in Brazil, so I went to the Bureau of Census to learn statistics there. And I went to a small group that was called Simulation Group. And the idea behind the simulation group, that I would say that today is computational modeling, was to consider the data of the exploratory data analysis and so on, but consider the census data and try to, instead of simply having, no, I don't have it, in simply having a regression curve, line, or tables, the idea was to present this data dynamically. So take the data and trying to guess the phenomenon behind the data, and then present in a computer program that would simulate the behavior, the several variables of this phenomenon. This was what was behind that. We're only partially succeeded that because we didn't have the computers, and we didn't have the knowledge to do that only start to be appearing in the 80s, 90s. Okay, so, but then I learned everything these years. I got my master in statistics, and I got my PhD in computational modeling. And I learned everything that I learned about general systems theory was then. So was very rich. And there was a cut in this. I finished my master degree in 75. And in 75, my boss asked me to really invent the national laboratory. I'm looking it backwards, really invent the National Laboratory of Scientific Computation. We didn't have words for that then. And so we had a laboratory of calculus, and what we did was no magic. We simply took the experience we got while trying to do this type of complex regression here, and we distilled that to the methodology, and we got something like this. And this is statistics, general systems theory, mathematical and computational and programming methods. And here, of course, the socioeconomic systems that we use to work there. And so, and to define what to do, we simply took this off and got something more similar. And in my thesis, I got a lot of programming. That's the only relevant part here. And that diamond is now, this is my reading backwards now. So we have observations, quantitative or not, formalisms to represent things and subjects of study and perspectives. And I consider system theory and organizations as perspective, the way you look to the world. It's more than anything else. Okay. Yeah. No. So after that, I went to the LNCC. I worked with traditional things, transmission line, fluid dynamics, and in tubes or not in the Amazon. But I had a non-disclosure project to study and build models for artificial lakes in the Amazon for electric power plants. And it took 2 years and a half and finished. But then when I was there, and I learned a lot about ecology. I'll tell you in a moment about this. I learned a lot about Amazon ecology and the landscape there. And it was pretty clear for me that the means that we had to describe that phenomenon are fairly insufficient. And I had the intuition that this is an interesting story. I had the intuition that we should add to the description of the phenomenon information, but not information as in physics, because information in physics, like entropy, are something that is ancillary. It's not you don't depend on the information to get the phenomena going. And here the idea was different. So the important thing that it took me 3.5 years of work, but I worked every day at least 1 hour. At least 1 hour, I stopped everything and thought about this problem, and I couldn't get rid of the Shannon formulas or Kolmogorov-Chaitin expressions of. I couldn't. It was absolutely a nightmare. I'll tell you a little bit about that later. And then I'll be back to this later, but this is important here. And the computers we had then is this big, and at the same time this small. You see, we have 4 megabytes of RAM, 32 of words of RAM, 32 bits each word, and 4 million instructions per second. Integer instructions, not floating point instructions. And so this is the picture of the region. And then I got immersed and absolutely fascinated by the Amazons. And yeah, I will be back to that. I'll describe here. The first thing is that my main interest, because I started with the lakes for the electric power plants, was in the flood of the rivers and the water in that region. And okay, one thing is the lake, and another thing is the fact that every year, due to climate regimes, there is a flood. And the flood in the high of the water can be near the mouth of the Amazon River. It varies around 6 meters. But up up basin, close to the mountains, it can vary 30 meters. Yeah, 30 meters. And then I'll get there. But before going there, this is also one thing that we developed in LNCC, that is the distinction between models and modeling. So the institute, the laboratory works mainly in modeling and generating different ways of producing models. And these are case studies, essentially, you see. So here is a picture for you to see that even when the waters are high, life continues. Even in the vegetation that is submerged partially, life continues, you see. And then, no, before that here. And then you see here, this is the measure of the water, the height of the water, where near this point here, somewhere here. No, here's Manaus, up here. And then we have variations that are as large from the little water to the highest water, 20 meters, more than that. What happens is that the vegetation during the high waters that we call, when the high waters come, the vegetation is submerged, but it continues to live. They don't die. They are adapted. And the result of that is that we get one trophic chain or one trophic web for the dry seasons and another trophic web for the rivers and a trophic web that is the flooded area that is collapsed between the two. So the phenomenon of the flooded areas, they go out and they change the trophic web of the system. In mathematical terms and system terms, it means that the interaction graph, the interaction term, the reaction term in general is a reaction term, it will change during the flood. This type of systems are known since the 70s or earlier 60s, but the way to handle them is to suppose that you know everything. That means suppose that you know all the three trophic webs, create a big trophic web, and then simulate things selectively in there. It's not a good thing to do mathematically, not this size, the size of the extent of the area, okay, because we need dispersion also. So this was the problem that I was facing, and I tried to solve with information, and essentially it didn't work very well. And then I discovered that the same thing occurs in the small size, you see, in the subcellular, intercellular regions, we have exactly the same type of variation in here is the trophic web becomes the biochemical network. Okay, so and it occurs, for instance, when you have a cell going from the mixotrophic to the autotrophic metabolism, and in many other situations. Okay? So it's general property of life living phenomenon. So now let's try to briefly tell you what I understand by organization. Okay, organization is something immaterial like energy, and is an idea that distinguish this to a pile of bricks from the house, in the sense that this is one organization, this is another organizations of the same set of atoms that are the bricks. Okay, so we have a big heap of bricks, we build a house, and the same bricks are here organized in this way, and here organized in another way. This is another example that where the elements that are here are the very same elements that are here because I deconstructed the image. And what differentiates one and the other is organization. What differentiates a pile of letters from text is how they are organized. So let's formalize that. I created, first of all, I forgot about the purpose of the organization. I forgot about the hierarchy. I forgot about the dependence on the surroundings, so everything. And I stayed with the three more important points that are associations, the atoms, and the way to create one from another. Okay, and then I have an informal definition of organization that is this one here, and you have to understand that an atom is something in the formal definition belong to an admissible set. So the atoms are the things that are logical atoms, not real atoms, are the things that we will not look inside at all. So this in this sense that I call this a perspective rather than anything else. Okay. So, but the key point is that while working with the whole path graphs, there are the mathematical structures that represent this. You have associations become hypergraphs. That is the more general way of relate things in mathematics. And I have to define this using concepts of logic, programming science, and all the things like that. This was formalized in that way. And with this, I got a space that, let me see, no, I don't have it yet. I got a space, that's a space of all possible organizations. And in these spaces, I can prove theorems about organizations as they are here, with no other interference from the outside, you see. And this is a gain over the system description, because you can only prove things in systems for one system, a special system there, and we don't have general results of about systems in general. Okay, so this is where I went, and initially I thought that this was information, and I tried to use this for 5 years without success. Then I realized that these were not information, they were organizations. And when I did that, I was able to very quickly define not so quickly, but relatively quickly, define organizations after I convinced myself that I could not define information without time. So this picture here is absolutely abstract. It has no space, no time, nothing, just relations. And when I discovered that I needed time, so I immersed these structures in the physical domain, in the physical, like molecules. Molecules are the paradigm of examples of organizations. Okay, so you think about a molecule like a formula or like a diagram. You have gamma, and if you think about the molecules that vibrate, you have the synexions. Okay, that is a functorial construction between gamma and the space, the physical space. So, and so these things here may be dynamical systems. It's pretty general because it is a perspective rather than anything else. So with this, was able to define information and define information based on a certain hypothesis. The first hypothesis that all living entity can be represented as a synexion. What's an organized volume or an organized thing. And then I have the perception hypothesis. That means when one organization or a signal is an organization itself. So when a signal arrives at the organization, it gets mapped somehow inside it. In the following sense, the signals alters this synexion internally somehow, where generally this is generally the memory. But a few days ago, I saw a paper where we have this same phenomenon even without DNA. So, of course, no brain. You have the chromatin around the DNA or RNA works in the same way because it shifts on and off certain parts, and these parts are expressed in a way or another. So mathematically, it's absolutely the same thing. So if another signal comes and then it's similar, and this similar is defined a posteriori, it will tend to be mapped in the same way, in the same place as the other one. So this is our hypothesis of working. So, and then later on, we have the interpretation. And to define interpretation, I need observers. But the whole of the observer here is very simple. The whole of the observer is just to say that something changed, something occurred. There is no judgment, nothing like that. So a good example of this, again, we'll go back to the molecules and to the docking of a molecule. So you have some big molecules that have some holes, and these holes, when you have what they call a ligand, the smaller molecule that gets in there, this ligand doesn't change appreciably the structure of the receiving molecules exactly like here, but it can change the properties a lot, particularly the vibrational properties of the molecule. And then, but this is really very, very it's very typical of what I understand by information here. See? And information is something that is relative because I need the observer to say that something occurred. And if I have two observers, one may see some different and the other one don't. And so one will say that there is information and the other there is no information. But then anyway, information separated like that is a signal that by interacting with an organization change it in an important way. Okay? How to observe this may be very complicated though. Okay? And of course, I have been using throughout here the idea of Rosen's idea about modeling, where you have nature entailments, coding and decoding into formalism, formal systems. Okay, so that's what I've done there.
Mauricio?
Yeah.
Sorry, we just have a question in the chat. What do you mean by gamma in this context? You mentioned gamma.
Gamma is the name of the space. Gamma is the name of the space that contain all path graphs. Okay? No. No, I don't have it here. But I've maybe done. No. I don't have it here. If I find it, I have a
we
picture
can
that...
We can also discuss it in the chat, but I mean afterwards.
Yeah. No, gamma is the name of this space, the space that contain all whole path graphs that are the mathematical representations of what I call organization. Okay, this is what they are, and then I can define functions in maps from gamma to gamma. I can define complexity measures that complexity measures that will attribute one number to each organization. Okay, so and then is the short story I would like to tell you very quickly. When I was working with that and looking for information, it took me 3 years and a half, and I was very amazed about that because I had all the elements. I knew everything, but I could not reach what I wanted. And this baffled me for 30 years till my daughter grew up. She is a neuropsychologist. And one day I was able, with her, talking over lunch, to express what was in my mind then. Okay, so we realized that there was a phase where I was completely lost intellectually, hitting, I call it a labyrinth, hitting the walls here and there, and I followed a line of reasoning, and I followed another line of reasoning, and I got stuck. And it was rather fractal, the impression I had then of where I was, is a fractal labyrinth, and I didn't know what to go or to do. And all of a sudden, I got a solution. And after the solution came, the world was different. The solution was exactly the definition of organization I've shown you. Information came later. But the idea is that the labyrinth that I was on was moving. This was because every time I made a trial, the landscape changed, the mental landscape changed, and that was really frightening. That was a tough time. That's a tough time, but it rewarded. It was, I think that it made me very happy. And at the end of that talk, and that's what's important for the next slides, we came to an ansatz, an empirical hypothesis, a conjecture, if you want. These are sloppy terms. That this phase of being lost in my thoughts in the labyrinth were necessary to modify my brain mind in such a way that I could see what I couldn't see before, that I could perceive things that I couldn't see before. And I'm working to refine this till today. I'm working to refine this ansatz. Oh, sorry. And now we come back to, with this in hand, I tell you why I convinced that we need to understand the scientific process, taking into account whatever we know about our brain-mind complex. You see, because the point is that I had all the system science elements, all the mathematical elements, all the programming elements that I used to build the organization, the whole path graph, I had before, but I could not see what I want. This is the point of that story and that hypothesis, and how I come here. And since I'm a modeler, the reason, just a remark, the reason that Shannon information doesn't work for biology is very simple. The set of messages is fixed a priori. So you cannot change it, you cannot modify it, and life is always learning. It's a learning thing. All living system is a learning system, okay? So this is where these things goes. And of course, if I have a group, I have to have communication. And here is where the Shannon-Weaver channels come in. Is a communication manner, and here is really a dialogue version of the Shannon-Weaver channel, because here I have a sender and receiver, and here I send the same. So I have here decoder, encoder, and so because the signals are going in both directions. And doing that, the message set is changed. It can be fattened, it can be made it thinner, but it changes. The meaning of certain here I'm not considering that, but I have another draw of the same channel where I consider the semantic and the semiotic levels here. And so the meaning of a message, of a signal, may change depending on how these guys here change, okay? So, and this is where I'm working now, and I'm trying to put the things to go on. And the basic reason I have, I call that artificial intelligence is not just AI, but we human beings that work in modeling, we are somehow artificial interpreters as well, because we choose what we see. You see that this is an important point in science. science is not about nature, but it's about observations of nature. Okay, so and this is where the brain come in, the taste, the pleasures, and everything there. We have to see the brain as a whole. And we are artificial interpreters as much as AI. Not the same, because we are conscious persons, and conscious and thinking here are beyond the reach of the automata. And I have to say one thing that I didn't publish yet, but the Turing machines belong to Gamma. Okay, so you can construct something like that, where in every point here I have a program. And this is also an organization in the sense that I give the word. Okay. And but this is not enough to understand the brain-mind complex. So far missing things. I'm working on that, and I'm working in fuzzy descriptions, because my daughter says to me that you cannot, when a person thinks, it's very difficult to map this thought in any region of the brain. Here's the brain, and is the spikes. Okay, here is the electromagnetic and the electrochemical pulses within the brain. So, and thoughts is something that is still, in my opinion, above that. So these are the atoms or the basic elements of the organizations that we may come to consider as thoughts or as thinking. Okay. So I'm about to finish, and then brain-aware learning goes back to to bring to this picture what's known in neuropsychology. And this we have always modeling here. And so this is where the artificial comes in, because modeling is always a choice process. You are choosing every moment what you are representing and how you are representing the stuff. So when we build theories, we never build theories about nature itself, but about the models that we created over the observations we have made in nature. Okay? And it's important to understand that is in these models here, there are many things that are not data. They are not quantifiable. They are not. They are observable sometimes. You see in my last slide that I have a way of observing organizations. Okay, I can construct an artifact to observe organizations. Okay, so a friend of mine said something very interesting that is here below, that the educational system, he said that in 2020, before this last AI wave. So the educational system built was towards mediocrity, with mediocrity in the sense of statistics. Okay, not in any cultural or emotional sense. This is mediocrity is what is in the mean. See, and with competitivity, but we need to address this question here. How can we teach the next generation to use AI wisely? You see, this is the key point. I have used it wisely sometimes, and when I'm not paying attention, it is a mess, complete mess. So it's myself, the same person. Okay, just if I'm not being, and then we can start discussing and answering these questions. Another thing that organizations does to us is that systems is classified in two things. We have two classes of things in systems. That is the thinghood, following Rosen classification, that are the things that are there. In systemhood, there are the things that glue the thing, the mechanism that glue the things together. Okay. Due to the recursive definition of organization, organizations blur this, because an organization can become a thing when it belongs to a higher level organization, and then we cannot talk anymore about thinghood and systemhood. We may talk about phenomenahood or something different, but the fact is that organizations belong to both. Okay, and I copied your message, the Jocelyn's message, that I found interesting. He is clearly a bright guy, and I know him. He's doing for a while, and he was able to very quickly in 1 month get the AI doing very nice things for him. But of course, I've seen things that were terrible doing by AI. So here I have the channel decomposed with the semantic level and the semiotic level. Okay, and this drawing here is Internet of Things that is itself a probe for organizations. Okay, not a place to explain it, but it can be done. It can be made done. Okay, so grounding the prevalence acts that we should investigate it, in my opinion, for the future. What makes our brain and minds adaptable to new things? And we can use AI to enhance it, and use AI also to do the things that will hamper our adaptability. What it is, I don't know. It's part of the things that I'm thinking now. But this is exactly what I meant to this project about the scientific milieu and the human brain. Okay. Thank you for your attention. Pardon me for overlapping my time.
Oh, thank you for that. Wow, lots of thoughts.
Sorry?
Lots of thoughts. Will you handle the questions in the, I don't know which Peter's going to handle the questions in the...
Yeah, so I'm happy for either Peter, but I'll start. I think we'll start with the chat then. So
Wow.
I will just, I mean, Alan, you have the straightforward question, the short, straightforward question, which is, Dr. Kritz, do you believe that information is fundamental? If not, why not?
What you mean by the first question? The first answer is another question. What you mean by information? You may have missed my first slide. And in my first slide, I was exactly saying that information has several senses, and these senses are different And then none of them, none of the formal senses we have of information match what we usually call information in the everyday life.
Well,
So,
if I may
and
explain what I mean.
in this sense, I have to answer you, no, it has no sense. But it's something that we need to deal with and understand much better than we do understand now to be able to go further in the future,
Okay. Well,
anywhere.
my remark, if I may, in information physics, and I've studied that, is then we say already that information is fundamental because everything has information in itself about itself, every cell, every particle, and therefore the link of information is fundamental. I think, yeah, also,
In that sense, yes.
right?
But that information is not even channel information.
Well, Shannon, of course, has information in quantification and so on without meaning. You maybe mean.
No, you need to transmit something to have channel information. And what you're talking about in physics is yet another information that I didn't list here. But it's true, there are 3 books by very around the 1990, and they talk about the information in physics and how fundamental they are. And this is a precious thing, but it's not the usual sense we are giving to the word now. But I agree with you that this sense must be taken into account so that we can have a better definition, if you want, or clarify the idea of what information is. Okay? I bring back Feynman, because Feynman, even force, you see, if you think about force among the physicists, this concept of force has changed enormously from Newton to Einstein and Feynman. And but even now, there are very subtle things. The energy concept is subtle. We cannot do really, if you go deep in the sense of the word, it's surprising. It surprises you all the time. So, but this is the beauty of science, that the beauty of science is that we can live with these doubts. We can live without being certain of things. And if you think that information is something that will certify you of anything, I must disagree.
Okay. Well, I'm just referring to work with having worked with Dr. Vopson in England. He says that information, energy, and mass are equivalent.
Maybe, but then we have to write them down in in the good perspective to see that.
It's interesting work, so just please look it up if you like. Sure, thanks.
Thank you. And some useful comments from Lynn. Thank you. Before I come to you, James, but Lynn is noting the distinction that you made between information as information and communication. So making that distinction. So I think there's something we might pick up on in the train of the discussion from Lynn there. But first I'll come to James, you have your hand up. Thank you, James.
Thank you. Mauricio, a very fine presentation. I've been working in very much the same area over the same topics here in the States with in much more fundamental ways with ISSS for the last 2 decades. Just a quick comment the notion of force, I've now used the term influence rather than force, because that carries both the neutral factors as well as volitional factors. But I just have one question for you. Bateson's phrase of information is the difference that makes a difference is a very nice poetic terminology, but I thought it was necessary to make that more scientific, and we don't really have that in science yet. How would you transfer Bateson's phrase into mathematics?
Sorry, how this? Your last question, how can you repeat that?
How would you translate Bateson's "the difference that makes a difference"? It's a pun in English. How would you
Yeah.
how would you transfer how would you
Puns are
trans
not the, sorry.
I'm sorry.
Yeah, puns are not easy to transform in mathematics, but
Well,
uh,
but in order to say that you don't agree with Shannon, and I'm with you on that. His definition is a very particular intentional motivation usage. But how would you translate the difference which makes a difference into a mathematical sense and a definition that is different from Shannon's?
my information, you mean?
Well, if you needed to make it a strict mathematical definition that's different from Shannon's definition, what is the
Yes,
smallest,
it is
for
different
example,
from
what is the smallest information bit? What is the smallest unit of information?
in my now of which information are you talking about? So it's algorithmic information or my information?
I prefer yours. How you would use it is to all sensibilities, whether it's organic or inorganic.
Um, it doesn't matter really because since it is a perspective of that. So if you consider just the molecules, okay, the smallest organizations, if you just a second, let me find it here. Yeah. Here. What the gauge here is what you consider as indivisible, as an atom or as your black box. So in any information that you define, that you construct, any whole part graph is ultimately grounded in this admissible set that is a choice of the modeler. So in this admissible set, I can have just atoms of the periodic table, or I can have particles, subatomic particles.
But
Okay?
if I asked you to make that into an arithmetic, not a physical representation, how would you put it into arithmetic?
Well, since this concept is not quantifiable, the arithmetics I have, the arithmetics that I can define, or so to speak, the type of manipulations, mathematical manipulations, operators, and things I have, they are defined over hypergraphs. So I can join hypergraphs, I can subtract hypergraphs, I can bind them, I can do a lot of things. But then I have to answer your question, I have to go down to more mathematics than I have shown about that.
Have you reviewed that? Have you gone into that area?
A little bit even in my 2017 paper, when I defined those things, I did that. So we can prove a lot of things in the space gamma, and you just using the complexity, but essentially the complexity measure, and the complexity measure for each element of this is a number, and here it is. So is a measure, is a function, normal from gamma into R plus. So any organization has a positive complexity, but there are an enormous number of organizations with the same complexity, and they are different.
Okay, I have one other question, which I was fascinated by, the flooding in the rainforest. The latitude of survival ranges for the flora and fauna in those extremes. Is there a general model that you have about that?
No, because there is not enough knowledge about that. The solutions, the biochemical solutions that we have there, the biochemical solutions we have, the biological solutions, are different. For instance, the plants that stay here, they may be submerged by 270 days a year.
Right.
So they are submerged, and it's not exactly hibernating, but they enter in a state of very low metabolism. And when the waters get down, they come to life again, including because normally the water there is very turbid. And the water and the light that comes in when the waters are high is very low. So what keeps these plants alive, it's yet unknown to the best of my knowledge.
I think that it's a very important topic, and I hope you and your students or whoever do some more research on that. I think it's an incredibly important thing.
Definitely, but it is up to the ecologists, you see.
Very good. Thank you so much for everything today. I love the entire presentation. Thank you.
Thank you very much.
Yeah, thank you. And that's a great discussion. So, Lynn, can I invite you to come in, please? Just because your comments are great. And I know you started from that idea of information. Lynn, is there anything you want to add or raise a question here?
First of all, I loved your talk, and it's so fun because the language you're using, I'm using different language often, but the same things. And I'm seeing when I wrote my book on the basics of system science, and I'm not a cyberneticist, so I don't put feedback in the center. It's not where I started, when I started learning about systems. So when I was writing my book about systems processes, I put information in as a process, and it took me 5 years to write my book, and I just got stuck on information because everything I read was just a mess, And every time I tried to finish the chapter, I read something new that made my mind just go. And then finally I had to stop reading anything and just finish it, But what I came down to is I first of all, yes. Shannon talked, and he said it for the first 7 or 8 years after his famous paper, said, this is a theory of communication, not information. Yeah. And that's absolutely true. And it's not messages I'm concerned with. It's the input that changes. It's the difference that makes a difference. It's input that informs me, literally forms a system. And then, of course, that changes the system. And so output changes. And that's where feedback comes in, output changes. And then that changes and informs the environment. So everything's constantly informing. So yes, information is fundamental, but it's not a thing. It's a process. So that's,
Yes, it's not a thing. I said since the beginning,
yes,
organizations is something immaterial. So it's a way of seeing things. You see,
exactly. Yeah,
if you have here the idea of information, for instance, that you're saying, it's in a certain sense, some kind of information is crucial for cybernetics, for the cycle of feedback. So you have having feedback. But the point is that think of a very big molecule with several dots, you see? Several places where small signals can come in, and it's much more like quite like our brains in terms of organization, and you are permanently getting new signals from outside and memorizing them. And when you do that, you change. If you
right,
think about a molecule, you see that. So the molecule will change the conformation, the spatial conformation, and the same signal, if the same signal, meaning the same uh, completely homolog molecule that comes in after that, they may be read completely different. You see, in the sense that the point where it will docks will be another one. And if it is another one, then the way this organism here, this organization here sees the surrounding is changed. So it's a process. So there is a very nice book saying that you cannot describe biology is a companion, is a proceedings of a meeting of several papers discussing that you cannot describe living systems without only with processes. You cannot think them of things as being things.
right.
See, so and then you have this this idea that everything flows. That goes back to Heraclitus, but there's it's really Pantare. So you everything flows in the interaction between flows um, is what matters. But this is something that this framework of organizations allows you to do because here we are. Because anything here, if you not the backbone, not the whole path graph, but the connections are meant to be that. So the connections are sets here that come from dynamics. They are all changing. So it's but how to describe that is case by case. You know, each case you have to design the things appropriately to see these things right. So it's a modeling process. Every time we are studying something, I have to go down to that.
As also as you have your triangle of observation, modeling, and theory, and I've been speaking for about 3 years with in conversations with Dwayne Hyberson, and he's writing about science, and he has exactly that same model. He hasn't finished his paper, but exactly the same model. And he's talking about science activity as the observation of,
Yeah,
yeah.
yeah. It's not really a yeah. I as I draw it, this is the external part of the science, no? But
Mm-hmm.
there is the internal part. If you add the internal part, you get a star.
Oh,
Bec-
interesting. You need
yeah,
to, I'm gonna, I took a couple of, I'm going to I want you to see his paper. I think you'd be really interested in it. I'm gonna take
yeah.
a
This is
screenshot of this one. and get it to Dwayne, because what
But
he's
this,
writing is
you
very
see,
important.
things are, when we need to go back to semiotics, because we are talking about external things. So he has its properties. So I don't know him, but or her, or
Him.
anybody
Yeah.
that's doing that. But we cannot see things much different. So we are talking about information, we're talking about force, and let me consider force. And I think, and I'm doing that because of the future and not because of multidisciplinarity. If you think about a physicist talking about forces, subatomic forces or macroscopic forces, they are talking about something that has something in common. And then you go to a social scientist, and the social scientists talk, oh, the social forces.
Right.
Well, there is something in common in those things, even though the mathematically or in the fine tuning things are different. So in the case, I have a hint for that, so that what we call force in general is something mystical, physical, subatomic, it doesn't matter, that provoke changes in movement, not in structures. Okay? So in the way things displace, and information with a knife, and for me is something that provokes anything that provokes changes in organizations, whatever they are. You see. So but we are missing that. You see that during the 50s and 60s and half of the 70s, people were trying to explain organizations in terms of information. So information cause organization. And you see that my solution is the reverse. I only can define information if I have after I had previously defined an organization. So this is, I think now and then about this, and I'm wondered, it's something that is fantastic. And I still don't understand that. I'm far from going there. But
Thank
this is
Yeah, thank you, Lynn, for that. Very helpful, I think, dialogue between the two of you. So thank you both for that. Gilham Kuczynski, looking forward to seeing where you are and what you have to say.
Where I am, I'm in the street. So, there's several things. Well, for one, I came in on the advice of Meg because she said I should look into what you're doing. And after listening to you, I really need to talk to you, but I can't do it here because I would talk for too long. I need you to talk further. So I'm trying to do something that's quite similar to what you're doing, although it's different because it's more deconstructed. But I'll explain later. The question I asked in the chat was, can we say learning is mainly about structural reconfiguration of interpretation?
almost
Almost.
because depend on the structural curves. Okay, and how it occurs. For instance, cancer is a change in organizations and in the forces that causes or maintains the organizations within an organism. And I doubt we should call it learning. So, but of course, if the changes is in regions of the organizations that will provoke a new behavior from that point on in relation to the environment, then I would call it learning.
Yeah, I think one does not contain the other. Like, not
Yeah.
everything is learning, but some of the reconfiguration might be called learning, and maybe all learning could be called reconfiguration of structure.
No, in this sense, I agree with you. Yeah.
Yeah.
All learning is reconfigurations of the structure, yeah.
Yeah, because if you just hear something and then you learn something, but you don't change anything about your structure, then either forgotten it or you learn nothing, right?
Yeah.
Yeah.
Is the case of the secretary. The example of the secretary in the beginning that I gave was well, it was not by hazard. You see, you send a message for the secretary, he has the message for one day, that matters, but she may never use it. And after that day, this become absolutely nonsense, and she forgets it. Okay, so
There's also something about the input conversation where I don't have a problem per se, but there's something about considering that inputs creates like change. I don't think you necessarily need input, because thinking in inputs is kind of externalizing systems, which to me seems anti-systems to some way.
That's it's very difficult to. I spent years learning to think in terms of organizations and synapses, and I'm still learning. So that's the problem is that the signal can come from inside.
Yeah.
It doesn't need you in this definition, you don't need a sender. The sender doesn't exist. It exists just the signal that would be analogous to a message. And this signal can come from inside. You're feeling tired, you're feeling hungry. So these are signals that don't come from the external world, they come from inside the organism or the organization.
How would you define something like, because there's the input idea from the exterior, but there's the idea of time configuration, like processes are bounded, are time driven, and so if some input or no input starts a chain reaction inside of a structure and system, and then it keeps reacting for some reason. I don't know if we're calling it signal or not in that sense, but like it could be a slow motion, it could be a very long reaction where there's a reconfiguration happening, where the system might be even learning, kind of like a metacognition. You could just think within yourself and somehow become smarter without really having,
Well, I understand your point, and this is a big complication because, of course, when I define information and I define information, it is an hypothesis that I have a signal and I have the imprint. Okay, the signal can be a molecule, can be an organization, but can be also an electromagnetic wave. So these are all organizations possible because I have the dynamical systems inserted in this. But one thing I couldn't do, and I tried for more than 5 years, was to define informations without considering time and change. So the time is there to say that something changed. Change in time are very tightly intertwined. If there is no change, there is no time. And there is no, and time is a way of describing changes.
Could you consider that structure is in itself information, and that it all, like, without thinking in terms of change, like, say you've got a complex structure, and inside of the structure is an information that is like a potential that can be uncovered to some extent, like discovery of physics. It doesn't have to move per se for you to discover a specific structure or in anything. And you could discover, say, a triangle, right? Like,
Yeah.
What I have to say about that's the following: any organization, any selection can be a signal. But a signal is only an information if it changes something. For instance, if you get the signal inside your memory and it doesn't change anything, locally it changed because you retained the information there, but an observer cannot see that. Then for an observer to say that this signal is an information, some change must be perceived by the information. So to say, in this case, to say that something is an information, a signal is an information, is a relative thing. So I may say that a signal is information, and a signal is information for somebody, for some organization, not for everybody. So not necessarily for everybody. And another thing that we have to see is that gamma, this space, it is I forgot to say that's important. It is a lattice. It is a lattice without superior element. So any organization is part of another organization, always. So in this sense that I say that a signal may reach one organization, or it may reach a group of organizations that is also an organization. It only will be an information for this collective organization, so to speak, if it changes something. But this is local. This is ad hoc. I cannot answer that in general.
yeah,
it's yeah. Okay, you carry on, Gil,
okay.
but and then
Okay.
I'll continue.
I'll just say that last thing and then I'm done.
Yeah, I hope you're on the way to a nice restaurant, by the way.
Yeah, I'm on the way to the subway, then Sainsbury. I was at the Royal Society, and yeah, it's tying information to an effect. But how about the idea? I don't know if it's a concept in systems or cybernetics of potential information, kind of like potential energy. Say there's an information inside the structure. It has no effect on anyone. It is perceived by nothing. It does nothing. But because it exists as a potential information, then eventually it has a potential effect if it is ever perceived. Right?
Yeah, that's okay. In reality, any organization is a potential information.
Yeah.
For
but in that
somebody
sense,
somewhere.
it would be distinct from time.
Because it would be potential. So this is more about the possibility for it to be.
Yeah. But it still exists.
But to define the equation, like to define the process in how it changes, I need the time. to recognize that it is an information, I need the time. But talking as you were talking in more general sense, in more general settings, so to speak, in larger organizations. So I'm start to see that there is another relativeness in information, that is the relativeness within the hierarchy of organization. So it can be that one signal is information for an organization that is part of another, and it is not an information for the bigger organization. You see, so or adversely, it can be no better to see that way. It's easier to see that a signal may be no information for a part of a larger organization, and be an information for the larger part. Larger meaning that one is part of the other. Okay?
Great. I think we could cut in there. I think, Margaret, I think maybe you go next. There are good comments from Malcolm and John in the chat. Also, Peter, I think it's normal for us to turn off the recording at some point. There's also something interesting from that I'm quite interested in surfacing about information and perspective, and the way in which, as we redefine information, we seem to be looking for different perspectives implicitly. But Peter, I think if we turn off the recording now and we just kind of get into later in the bar mode for the last 20 minutes or so, hand over to you, Meg, as you have your